so the next speaker is Arun Pandyang. He's going to talk about deterministic and stochastic properties of really Taylor mixing with a power law space dependent acceleration.
Hey, so I would like to present this work which I did with my colleague Nora Swisher, who unfortunately could not be here, and my advisor Professor Snejana, who fortunately could be here. It's very fortunate because now if you have questions after the talk, she can directly answer it. So the work we did, so we wanted to develop a model that describes Rayleigh-Taylor mixing when acceleration is non-uniform, and then we also wanted to describe their deterministic and stochastic properties. So just to reiterate, RTI develops when fluids are accelerated against their density gradient, and this leads to interfacial RT mixing. Now, in nature, a lot of times in RT flows, the acceleration is variable, but when at the time we started doing this work, we noticed that a lot of work was done where people are studying acceleration as being uniform, so we wanted to sort of study this non-uniform acceleration where, so we took two cases where the acceleration was a power law function of time or in space. So this work mostly describes the latter. So we used the momentum model of RT mixing, which was originally developed to describe RT mixing with uniform acceleration, but we extended it to describe a non-uniform acceleration. So basically, for a parcel of fluid per unit mass, its dynamics is determined by two things. One is the momentum that it gains due to buoyancy, and the other one is the momentum it loses due to a drag. So per unit mass, you have a resultant acceleration of the rate of momentum gain, which is a power law function in space, as I already mentioned, and the rate of momentum loss, which is given by CV squared over L, where L is the characteristic scale of energy dissipation. In RT mixing, the dominant scale is the vertical length scale. So this is essentially CV squared over H. And we get solutions both in space, where time is a parameter, and also in time, explicitly in time, for both the vertical amplitude as well as velocity. So now if we treat drag as a stochastic quantity, we get these two equations directly comes from the momentum model, and we get this third equation under the assumptions that the drag coefficient C is a stochastic process with stationary log normal distribution, which it reaches at a characteristic time tau, and the fluctuations are generated by a standard Wiener process. Now, we also know that there are, from this model, that there are two subregimes depending upon purely the acceleration exponent, m. There is a critical value that's given by this expression, where C is the mean value of the drag coefficient. If your acceleration exponent is above this critical value, then your solution exponent and your solution, then you are in the acceleration-driven regime, and your solution exponent and the solution prefactor in this regime would be both dependent upon that acceleration exponent m. Now, if you're in the other regime, which is the dissipation-driven regime, then where basically your acceleration exponent m is less than your m critical, then your solution exponent would depend on the drag coefficient, and your solution prefactor will depend upon the initial conditions. These properties actually persist even if you express the solutions in space. Once again, you have two mixing regimes, the acceleration-driven mixing regime and the dissipation-driven mixing regime, and depending upon your acceleration exponent purely. And once again, your solution exponent in the acceleration-driven mixing regime depends upon the acceleration exponent, and your solution prefactor also depends upon your acceleration exponent and not the drag coefficient. And in the dissipation-driven mixing regime, your solution exponent depends on the drag coefficient, and the prefactor depends upon the initial conditions again. As we saw, this is the same case for the solutions in time. So we decided to solve these equations numerically. So we wrote a solver, ran it on a supercomputer for about 1,000 trajectories over 1 million time steps, which took about a week or so. Although I believe now it is faster because essentially these trajectories are independent of each other, so we can sort of run them in parallel. So we tested a broad range of parameters for the acceleration exponent. We let them range from both sides of the M critical, so because we wanted to get some cases from the dissipation driven regime as well as the acceleration driven regime. Because our for the C mean we chose, our M critical was -8, so we chose its values from both sides. And as I already described, our C is a log normal process, and it has a log normal distribution, and the standard deviation we chose was half of the mean value. So we got solutions that are power loss so this describes the solutions in time. This is also the case with solutions in space. As you can notice, the amplitude in both acceleration driven and dissipation driven mixing regimes always increase, but in the acceleration driven mixing regime, the acceleration dominates as you would affect the dynamics of the system, while in the dissipation driven mixing regime, the acceleration doesn't play an important role. We also found that for the solution prefactor, which is in green here and in here, which is scaled by their theoretical values, they are more sensitive to the noise than the values of the exponent, the solution exponents. And yes, and we were we were able to easily identify both of them. Also, we found out that so this is a solution in space. Now here also the solution prefactor is way more sensitive to noise than the solution exponent, but both the solution prefactor and the exponent are both way more sensitive than the solutions in time, which is interesting. We also have another result, which is that both these regimes have their own characteristic invariant, which is a quantity that's dimensionless, and in their respective regimes is around 1. So now in the dissipation driven mixing regime, this value is scaled by V dot, it's this expression, and in the acceleration driven mixing regime, it's scaled by the effective acceleration G, and it's given by this expression. And graphically that looks like this. So in the acceleration driven mixing regime, the values are very close to 1, and in the same expression and for the same quantity in the dissipation driven regime, in this insert here, it diverges. And likewise, the invariant for the dissipation driven regime is very close to 1 in that regime. For M is -9. If you remember, our M critical was -8, so we are in the dissipation driven regime here. And now if you look at the same quantity in the acceleration driven regime, it again diverges. So this is a good way of sort of knowing which mixing regime you are currently in. Now, so in conclusion, like I said, we wanted to develop this model that would describe RT mixing when acceleration is non-uniform, specifically when there are power law solutions in time or in space, and we found out that we have self-similar power law asymptotic solutions both in time and space, and whether they're in time or in space, the solution prefactor is more sensitive to noise than the solution exponent, and the solution in space is more sensitive to noise than the solutions in time for both the prefactor and the exponent. And then there are two distinct mixing regimes, the dissipation driven and the acceleration driven regimes, each of which have their own characteristic invariant value. That's it. Thank you.
Questions? Could you just go back to the equations you were solving with your computer program?
This one?